Hello and welcome to this manufacturing process technology part 2 module 43. We just discussed in the last module about the von Mises criteria, which is based on the work of deformation, and what it assumes is that the strain energy generated per unit volume should be above a certain critical energy for the yielding to happen. Okay. Now this criteria came out in 1913, but there was a criteria earlier to that, which in fact I should have done earlier, but because of the sequencing of the lectures it was like this. Way back in 1864, which is also known as the Tresca criteria. So we will try to now analyze that, and it is based on shear stresses basically. Okay, so we will call this Tresca yield criteria, and I will first write down what the criteria is, and then we will try to see how the proof exists or how we can actually find out the maximum shear stresses, etc., particularly in a system of stresses which has both shear as well as principal stresses acting together. So this was in 1864. Okay. The criteria says that the plastic flow will take place when the maximum shear stress exceeds the critical value. So here this is actually more like the shear stress model, earlier it was the energy model. So the energy model really yields a more accurate estimation, I would say, of the shear maximum shear stress in comparison to the Tresca's criteria. But still it is important to have a look at what is this maximum shear stress criteria, and for that we need to understand certain things related to how in a multi-axial state of stress, when there are shear stresses and there are principal stresses, what are the kind of issues which are involved in a block element. And let us consider a block element here where there are principal stresses as well as shear stresses. So let us say it is a plane strain problem that we are wanting to evaluate, and we have the principal stresses sigma x and sigma y, and also the shear stresses tau yx and tau xy, and similarly the balancing stresses on the balancing shear stresses on the other side of the block. Here we consider a plane along an angle theta represented by the diagonal with respect to one of the sides, where we try to evaluate what is the effective stress which is there. So here the goal really in this whole block element is to be able to find what is going to be the maximum principal stress on any one plane at a certain angle theta, and what is going to be the maximum shear stress actually. So our final goal in the Tresca's criteria is to have an estimate of when will the plastic flow start by looking at that maximum shear stress. And so because of all the different principal stresses and the shear stresses which exist in this system, there has to be a certain plane at a certain angle theta where the shear stress would be maximum, and so we will try to obtain that plane mathematically and try to find what is the maximum value of the shear stress, and then equate that value in a commensurate manner so that this can be equated to the ultimate yield stress of the material, and that will fulfill our yielding criteria for the Tresca's case. So that is exactly what we are trying to do here, and for that we would look at particularly this shaded triangular element as I have drawn in this half of the block. Okay, and let us actually look individually at the different stress components and what is going to be the overall stress in a plane which is at an angle theta with respect to the side of the block. So let us say one side faces a principal stress sigma x, another there are two components of shear strain here, one is tau xy, another is tau yx. Okay, and then there is also another principal stress sigma y that this block faces. So let us find out what is going to be the overall stress, the principal stress as well as the shear stress in this plane. So we are more interested in obtaining the stress in this direction as well as in this direction, owing to this particular plane strain problem. and then we would like to do some optimization here for different values of theta, where in one case the sigma would be the maximum and in another case the shear stress would be the maximum, and then we will take that particular angle where the shear stress will be maximum and try to compute what is the shear stress value. So once we have done all that, then we arrive at this yield criteria of the shear stress value exceeding a certain critical value for the material for the plastic flow to happen or the yielding to happen. So that is basically the whole strategy that we are going to develop here. So here let us look at a coordinate frame. Let us say this is actually the conventional xy coordinate frame, and we are talking about just changing the coordinate frame into another frame which is perpendicular and parallel to this plane. So let us record this element as OAB. So we are talking about the plane AB, and we are talking about a coordinate system which would be exactly perpendicular. So let us call that x1 direction, and parallel to the plane AB, let us call that y1 direction. We have the normal coordinates, so the normal plane again represented here as x and y, just as I did here, okay. And the idea is that this can be thought of as if the normal coordinate has moved by an angle theta to generate this x1 y1 modified coordinate, etc. And then let us now try to evaluate the sum of forces in the x1 direction, okay. So we assume that this particular block element here is unit length into the page, and therefore the area of cross section that this block element would have is unity in the z direction times the whatever is the length component AO or AB, okay, OB, or as a matter of fact AB. So this is how we will try to formulate the problem. So let us say if we want to compute in the first instance the sum of forces in x1 direction, so we are left with a balance of forces in x1 which is due to sigma x1, for example, okay. So let us say the total amount of force on the plane AB should be actually equal to the, if I look at this area because of OA, so OA times of unity is the area, and we want to see what is the area AB times of again unity, because this block is unit length into the page, okay. So the relationship which would exist is that OA should be equal to AB times of cos of theta, or the area of this plane AB, so area of plane AB, okay, should be actually equal to the area of plane OA divided by cos of theta. Or if you assume this to be equal to, let us say, area A, so this is A secant theta. So we want to find out what is the overall force due to the stress, principal stress in the x1 direction. So sigma x1 times of A secant theta is one of the forces, and then there are many other forces on this particular point because of several of the components like sigma x, sigma y, and similarly tau ix and tau xy. Let us just record individually all these forces. So the force applied here in the direction x1 would actually be equal to so we assume that the block does not change in shape or size, or there is no distortion so far. So the force balance is recorded here till the distortion starts happening, okay. So in the x1 direction, the sum of net forces in the x1 direction should be equal to 0, okay. The sum of forces in the x1 direction at this particular point is going to be equal to 0. So minus of sigma x times of A cos of theta, okay. So again the sigma x A is basically the force acting on the plane OA, and this force we are going to translate by an angle theta in exactly the opposite direction. So if I translated this in the opposite direction, this will come in this direction here, right here, okay, and this can be recorded as sigma x times of A and cos of theta, but negative in the direction of sigma x1 A secant theta. So minus of sigma x A cos theta, minus of, similarly we have tau yx times of A sin theta, minus of sigma y times of A tan of theta times of sin theta. Please understand this, we are talking about a case where we are wanting to measure the contribution because of sigma y, and this being the area A, OA, the component OB obviously would be OB into 1 maybe is equal to OA into 1 times of tan of theta. So because OB by OA should be equal to tan of theta, okay. So therefore the area of the face OB, let us say area of the face OB should be equal to the area of the face OA, which was actually represented at A in the last case, times of tan of theta. So we are talking about a total amount of force sigma y into A tan theta on this particular face AB, and this force is in this particular direction, and we are simply trying to take the component of this force in the x1 direction meaning thereby now this angle is theta, and obviously this is 90 minus theta, okay. So this is 90 minus theta. So we are taking the component of this force, meaning thereby this times of cosine 90 minus theta, and cosine 90 minus theta is basically sine of theta, okay. So that is why this term exists, minus of tau yx times of A tan of theta in a similar logic, in a similar manner, times of cos theta should be equal to 0. So having said that, now I know that, I mean we already know that in this particular case, if the block does not distort or deviate, both these components tau xy should be equal to tau yx, because they are like cancelling components with respect to each other. So therefore I should be left with an expression for sigma x1, which is equal to 1 by secant theta times of sigma x cos of theta plus tau yx sine of theta plus tau y tan of theta sine of theta plus tau xy times of, you can actually replace this with yx because obviously they are equal and opposite to each other, equal to each other. So you have tau yx times of tan of theta times of cos of theta, and this can also be represented as theta, I am sorry, this is sigma. This can be also represented as sigma x times of cos square theta plus sigma y times of sine square theta plus twice tau xy sine theta cos of theta. Similarly, we will do the sum of forces less than the x1 direction in the y1 direction. So I am going to now first try to represent this in a little more better manner. So we are going to substitute for the various values here. So we already know that this cos square theta can be represented as, so twice cos square theta minus 1 is cos 2 theta. So we just represent it in 2 theta terms. So therefore cos of square theta should be equal to cos 2 theta plus 1 by 2, okay. So that is how I am going to represent. So this is cos of 2 theta plus 1 divided by 2, plus again similarly I have 1 minus cos of theta by 2, 1 minus cos of 2 theta by 2 as sine square theta plus tau xy times of sine of 2 theta, okay. So because twice sine theta times cos theta is sine of 2 theta, and this is how we should be able to represent sigma x1. So if I just substitute or algebraically manipulate the different terms of this particular expression, we have sigma x1 equals to sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 cos of 2 theta plus tau yx sine of 2 theta, which is the effective shear stress or effective principal stress in the plane or in the principal plane, which this plane is actually, the plane AB is known as the principal plane. So the effective principal stress in the principal plane, okay. Now whether this is maximum or not is actually dependent on a condition where we would like to differentiate the overall stress in the x1 direction with respect to theta and try to say and try to equate it to 0 and say what is that angle corresponding to which the principal stress in that particular plane will be maximum, and in fact that angle is generally taken as the angle of the principal plane, okay, of the particular block. So when we try, okay, so now before proceeding I would also like to sort of go ahead and do the similar summation of forces of that particular block in the last slide in the y1 direction, just as we did in the x direction. And here in the y1 direction I would record tau xy or you can say x1 y1, which is the shear stress along the AB plane. Okay, so let me just write it down here for a little more clarity. So we were talking about sigma x1 in this direction, and this particular is stress is the shear stress in that x1 y1 plane, which I am recording as tau x1 y1. So here the tau x1 y1 times of a secant theta plus sigma x a in the same manner, in the same logic that I have done in the last module, sigma x a times of sine theta minus of tau xy a times of cos of theta minus of sigma y times of a tan of theta times of cos of theta minus tau yx times of a tan of theta times of sine of theta should be equal to 0. And from here I can obtain the tau x1 y1 or the total shear stress in the plane AB. So shear stress in the plane AB to be equal to minus of sigma x minus sigma y by 2 sine of 2 of theta plus tau xy times of cos 2 theta. You have to just do in the same manner as we did before in order to obtain this expression here. Let us call this expression 4, which defines the shear stress in the principal plane. So we have now one expression which is defining the maximum principal stress in the principal plane, or the principal stress in the principal plane, or the let's say the plane AB. Right now let's not confuse that with the principal plane, because it will correspond to that value of theta where this stress is maximum. So let us say plane AB. So we are finding out the principal stress along the plane AB and the shear stress along the plane AB, and these are represented by equations 3 and 4. And now we have to look at the maximization problem here, where we try to actually find out what is that plane AB at an angle theta where the principal stress is maximum. So let us look at this now. So here, for example, in this case, if we differentiated the first term sigma x1 with respect to d theta, we would obtain sigma x minus sigma y by 2 times of minus twice sine 2 theta plus tau xy times of twice cos of 2 theta equal to 0 for the maximization condition. And this happens when the tan of 2 theta, and let us call this the principal plane, okay, because here is where the principal plane is really the plane where the principal stress is the maximum, okay. So that comes at an angle theta p equals or given by tan inverse of twice tau yx by sigma x minus sigma y, okay. That is how you are recording the principal plane's direction. So we can think of it as a an angle here, right here, twice theta p, where one side has a stress sigma x minus sigma y, another is twice tau xy, so that you have a and tan of 2 theta p is basically given by this twice tau xy by sigma x minus sigma y, and the overall value, or the, let us say, the hypotenuse value here is 4 times of tau xy square plus sigma x minus sigma y whole square, whole under the root, okay. So I have now, I can record what is sine theta and cos of theta. So sine of 2p and cos of 2 theta p can be recorded as perpendicular by hypotenuse and base by hypotenuse respectively. So this becomes equal to twice tau xy by this whole term root of 4 tau xy square plus sigma x minus sigma y square, and sigma x minus sigma y divided by root over 4 tau xy square plus sigma x minus sigma y square whole under the root. Okay, so that's how you record sigma sine 2 theta p and cos 2 theta p. Now therefore by putting one value of theta p, we can try to find out what is the maximum sort of sigma x1 at this particular plane, which is corresponding to this 2 theta p, to find out what is the maximum principal stress coming. So let's evaluate the value of sigma x1 at this particular theta p 2 theta p plane, which is corresponding to the principal plane. So we have here the expression written as sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 times of cos of 2 theta, which actually can be recorded as sigma x minus sigma y divided by root over this 4 tau square xy plus sigma x minus sigma y whole square plus again tau xy times of sine 2 theta, which can be recorded again as twice tau txy divided by root over 4 tau xy square plus sigma x minus sigma y square, in a manner so that when we compute all this together, the value would actually come out in this case as finally sigma x plus sigma y by 2 plus root over sigma x minus sigma y by 2 whole square plus tau xy square. So that's going to be the maximum value of the sigma x1 at the plane or the principal plane which is at an angle theta p with respect to the sides of the block. Okay. Similarly, if I were to look at what is going to be the maximum value of the shear stress and try to find out whether it is going to be in the same plane or a different plane, you will record that in this case the plane completely changes and the maximum shear stress doesn't come in the same plane as the principal the plane actually. So we call that the maximum shear plane, and let's actually look at that value of theta. So we already have recorded that the tau x1 y1 which is the value of the torque or value of the overall shear stress at the plane AB, okay, of our geometry. So already we have described the tau x1 y1 to be equal to minus sigma x minus sigma y by 2 times of sine of 2 theta plus tau xy cos of 2 theta. We have described this in the earlier section here when we talked about the shear stress in the plane AB. So let's now look at the maximized condition of this shear stress and find out whether the theta would be the same theta p or some other theta based on just this derivative equal to 0. So we do del or d tx tau x1 y1 by the theta here, which is actually equal to again minus of sigma x minus sigma y cosine 2 theta minus of twice tau xy sine of 2 theta equals to 0, and the condition that emerges here is basically corresponding to tan 2 theta, let's call it theta s, which is actually the shear plane, is equal to minus of sigma x minus sigma y divided by twice tau xy. If you record, tan 2 theta p had earlier been found out as a completely different plane, which is twice tau xy by sigma x minus sigma y. So basically you can think of it that it's actually the inverse. If I look at value wise, it is really the inverse of the of the principal plane. So theta is definitely not equal to theta p, and it basically means that the maximum shear. So there's an interpretation here that the maximum shear stress in such a plane within the block may not be or is definitely on a different plane or along a different plane than the maximum principal stress. In fact, I mean, we can show here that if I substituted the value of this 2 theta p tan 2 theta p back into the of the total amount of shear in the plane, you will see that in particular this particular plane the shear doesn't even exist. Okay, I mean I can probably put this value here and show. Let me do that in the next step, but the conclusion here is that the maximum shear stress in such a plane within the block is definitely along a different plane than the maximum principal stress or the principal plane. Okay, so we call such a plane where shear stress is maximum, the maximum shear plane. In fact, what we are more concerned with is this maximum shear plane, because here is where the Tresca criteria needs to be applied for any kind of stress condition, multi-axial stress condition to a particular block system. Corresponding to a angle theta equal to theta s, the stress gets, or the shear stress gets maximum along this plane, the maximum shear plane. Okay, and so that maximum stress should be able to cross over the yield stress for the yield criteria to satisfy, or the plastic flow to begin basically. So that is what the whole purpose of this exercise is, or the Tresca is. So let us look at what is that criticality, or what is that condition corresponding to which this will happen. So before doing that, I would like to just try to evaluate certain issues here. One is that what is going to be the state of, let us say if let's talk about the principal plane. So what is going to be the state of stress or state of shear stress on the principal plane. So as we have all recorded that corresponding to let us say tan twice theta p, which is actually equal to twice xy by sigma x minus sigma y. Other words, let us just also write down both the causes and the sines of twice theta p. So one is twice tau xy by root over 4 tau xy square plus sigma x minus sigma y square, and the other is basically sigma x minus sigma y divided by root over 4 tau xy square plus sigma x minus sigma y square. Okay, so having said that, if I put this value of the principal plane in the shear stress equation, which is again given by the tau x1 y1 along the plane AB is minus sigma x minus sigma y by 2 sine of 2 theta, okay, plus twice or tau xy times of cos of 2 theta. So at let us say theta equal to theta p, or along the principal plane, if I calculate what is going to be the shear stress theta equal to theta p, this comes out to be equal to sigma x minus sigma y by 2 times of this sine value twice tau xy by root over 4 tau xy square plus sigma x minus sigma y square, okay, plus tau xy times of cos of 2 theta p value. So I am just substituting theta equal to theta p here, sigma x minus sigma y divided by root over 4 tau x square or tau xy square plus sigma x minus sigma y square. So obviously these are equal and opposite to each other, and the whole shear stress at the principal plane becomes equal to 0. So one conclusion that we have is that along the principal plane there is no shear stress component. Conclusion is that the shear stress along plane AB, shear stress along the principal plane, in fact that is the reason why it is called principal plane, so one is that the shear stress along the principal plane is 0. Okay, so reason for it being called principal plane. So only the principal stress exists there. Now the plane of maximum shear will not show this in this kind of a situation, because in the plane of shear you do have average force and average principal stress which exists, which is actually equal to sigma x plus sigma y by 2, and we can see that by just substituting the value of theta equal to theta p or theta equal to theta s in the equation for the principal stress sigma x1. So if I say sigma x1 equals as I had earlier recorded sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 times of cos of 2 theta plus twice yx times of sine of 2 theta, and then substitute the value of theta equal to theta s, that means along the maximum shear plane what is going to be the value of the principal stress. We find that it is a non-zero value. So if I just let us say put this theta equal to theta s, let us calculate. So we have sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 times of cos of 2 theta s, which is again as I had illustrated earlier equal to tau xy by root over sigma x minus sigma y by 2 square plus tau xy square. Remember, we had called about this angle twice theta s, the maximum shear plane angle, as the tau xy and minus of sigma x minus sigma y by 2. Okay. So so basically these are the definition in the angle is described by a triangle where the stress is sigma x minus sigma y by 2 and twice or tau xy are both arms of this right triangle. The sine and cos terms can be again found out as so we have to calculate what is the hypotenuse here, which is sigma x minus sigma y by 2 square plus tau xy square whole under the root. So that's how we arrive at this term here for cos of 2s and sine of 2s. So let's just put that value as well. Sine of 2s becomes equal to minus of sigma x minus sigma y divided by 2 divided by root over sigma x minus sigma y, just modify this here, by 2 square plus tau xy square. Okay. So that's how you substitute and try to calculate, and if I actually calculate all these values, these two terms eliminate out, okay, and we are left with only sigma x plus sigma y by 2, which is actually the state of an average principal stress. So in the maximum shear plane, it is very wise to conclude that at an angle corresponding to theta equal to theta s, the principal stress doesn't go down to 0, but definitely this is the plane along which the shear stress can be maximum. So then we will maybe in the next module take up this issue, that what is that criteria which will allow the yield or the plastic flow to happen given all this calculations so far, so that the maximum stress exceeds beyond a certain ultimate yield stress criteria. So with this I will like to close this module, and in the next module we will discuss more on the Tresca criterion. Thank you so much.